Okay, we're recording, and we are working on module 4 today. I apologize about the cough. Apparently, I just get to have that for a while. So, today we're talking about data acquisition fundamentals, different types of data acquisition formats, and data acquisition methodology. Here's our flow of the module. And like I have been doing, module 4 will be out there in the link, the little PNG screenshot captures after class. So, data acquisition. This is the use of established methods to extract electronically stored information from suspect computer or storage media to gain insight into a crime or an incident. Investigators must be able to verify the accuracy of the acquired data, and complete process should be auditable and acceptable in court. So that's our big thing, remember. And by auditable, they mean that they should be able to backtrace all the steps and repeat the same process and get the same results. So there are two types of acquisitions. There's live acquisition, which involves collecting data from a file or system that is powered on, and dead or static acquisition, which involves collecting data from a system that is powered off. So in live data acquisition involves collecting volatile data from a live system. Volatile information assists in determining the logical timeline of the security incident and possible users responsible. Live acquisition can then be followed by a static or dead acquisition, where an investigator shuts down the suspect machine, removes the hard disk, and acquires the forensic image. So the types of data captured during live acquisition: for system data, you have current configurations, running state, date, time, current system uptime, what processes are currently running, who's logged in, DLLs and shared libraries, swap files and temp files. And then network data, you have your routing tables, ARP cache, network configuration, and network connections. So this is a very good slide. It's called the order of volatility, and I really like the way they have this listed out in a nice visible system. When collecting evidence, an investigator needs to evaluate what's called the order of volatility of data, depending on the suspect machine and the situation. Now, order of volatility is not just limited to digital forensics. It has to deal with any forensics, but this is how you set it up with digital forensics. So according to RFC 3227, this is an example of the order of volatility for a typical system. You have your registers in your cache, your routing table, process table, kernel statistics and memory, temporary system files, disk or other storage media, remote logging and monitoring data that is relevant to the system in question, physical configuration and network topology, and then lastly, archival media. So, just looking at this, do you think you understand why registers and cache are up top versus why archival media is at the very bottom?
Yeah, the danger to them.
I can't hear you. What?
Yes, the danger to them being destroyed.
Exactly. Exactly. And that is also the same thing when you're talking about any sort of volatility with forensic data. It's the danger to being destroyed, or like if you're talking about DNA evidence, it's you need to get the DNA evidence that's either, you have to combine what's going to be most important, but you also have to combine it with how quickly it can degrade. So this is kind of the same thing. These things degrade or disappear faster, so they're more important, whereas archival media, you can do a static investigation on, and it doesn't go away as quickly. Dead acquisition. So this is defined as the acquisition of data from a suspect's machine that's powered off. Dead acquisition usually involves acquiring data from storage devices like hard drives, DVDs, USB drives, flash cards, and smartphones. Examples of static data are emails, Word documents, web activity, spreadsheets, slack space, unallocated drive space, and various deleted files. So what are some rules of thumb for data acquisition? So we've gone over this one over and over again, and you're going to see this all over. Do not work on the original digital evidence. Create a bitstream logical image of the suspicious drive or file to work on. Sometimes they call it a bit by bit copy, and that just literally means that you're making a clone of that. Then produce 2 or more copies of the original media. So you have what's called a working copy, and then the other copies act as library or control copies that are stored for disclosure purposes, or in the event that the working copy gets corrupted. Use clean media to store the copies. You wouldn't think that's something you would have to remind people of, but it really is. You can have, you know how all the things that you're looking at, a lot of the times we pull up partial files and things like that. Well, if you store your archival copies on something you've used before, well, what happens if you accidentally mix up 2 cases then? Then there goes your issues. And then upon creating copies of the original media, verify the integrity copies with the original. So do you remember when we were doing that Geiger program, how one of the checkboxes was integrity, verify integrity? That's what they're talking about. Next, different types of data acquisition. So there's logical and sparse acquisition. Logical acquisition allows an investigator to capture only selected files or file types of interest in the case. Examples of logical acquisition include email investigation that requires a collection of Outlook PST or OST files, or collecting specific records from a large RAID server. Sparse acquisition is similar to logical acquisition, which in addition collects fragments of unallocated data, allowing investigators to acquire deleted files. Use this method when inspection of the entire drive is not required. A lot of times you'll see this if like you're having to do, let's say your case involves this huge server with a RAID array with just tons of drives on it. A lot of times they will start with a logical and sparse acquisition to comb through things, because you kind of have to narrow the net. Otherwise, you're going to end up looking at everything and it'll take so long that your statute of limitations run out and the case gets tossed anyway. Okay, bitstream imaging. Bitstream imaging creates what's called a bit-by-bit copy of a suspect drive, which is a cloned copy of the entire drive, including all its sectors and clusters, which allows forensic investigators to retrieve deleted files or folders. Bitstream disk to image file. It is the most common method used by forensic investigators. The created image file is a bit-by-bit replica of the suspect drive. And then there's a list of some tools you can use: ProDiscover, NCase, FTK, SleuthKit, Xways. There's a whole bunch of different ones. Bitstream disk to disk. Disk to image copying is not possible in situations where the suspect drive is very old and incompatible with imaging software, or the investigator needs to recover credentials used for websites and user accounts. To overcome this situation, investigators can create a disk to disk bitstream copy of the target media. While creating a disk-to-disk copy, investigators can adjust the target's disk geometry, that's its head, cylinder, and track configuration, to align with the suspect's drive, which results in smooth data acquisition process. And there are EnCase Tableau forensic imagery. And the reason there's less of those is this is a little bit more difficult to do. So it's a little more specialized. EnCase, you'll see that one listed quite a few times. They have an entire suite, but you can also get just certain chunks of it as well. Determine the data acquisition format. Okay, so there's what's called the raw format. This is our bit by bit copy of the suspect drive. Images in this format were usually obtained by using the DD command. What are the advantages? Well, it's fast. It has a fast data transfer. Minor data read errors on the source drive are ignored, which is why it's fast. And it is read by most forensic tools. What are the disadvantages? Requires the same amount of storage as the original media. Tools are mostly open source. It might fail to recognize or collect marginal or bad sectors from the suspect's drive. There's what's called proprietary formatting, and that just means that it's one that this particular tool created. Commercial forensic tools acquire data from the suspect drive and save the image files in their own formats. They offer certain features, which include option to compress the image files of the evidence or disk drive in order to save space on target media, ability to split an image into multiple segments in order to save them to smaller target media such as CDs or DVDs while maintaining integrity, and the ability to incorporate metadata into the image file, which includes date and time of acquisition, hash values of the files, case details, etc. What is the disadvantage? Well, the image file format created by one tool may not be supported by other tools, obviously. That's why it's called a proprietary format. Then there's AAF, or AFF, sorry, Advanced Forensics Format. This is an open source acquisition format with the following design goals: no size limitation for disk to image files, option to compress the image files, allocate space to record metadata of image files or segmented files. It's got a simple design and it's customizable, accessible through multiple computing platforms and OSs, internal consistency check for self-authentication. And the file extensions for this are AFM for AFF metadata and AFD for segmented image files. And then there's the AFF4, which is just the more advanced version. Redesign and revision of AFF to manage and use large amounts of disk images, reducing both acquisition time and storage requirements. Basic types of AFF4 objects are volumes, streams, and graphs. They're universally referenced through a unique URL. Abstract information model that allows storage of disk image data in one or more places while the information about the data is stored elsewhere. Stores more kinds of organized information in the evidence file and offers unified data model and naming schemes. All right. Lastly, understanding data acquisition methodology. So this is a nice little one that's got a good flow chart to it. So to start, determine the data acquisition method. Select your tools, sanitize the target media or use brand new media. If the computer is on, that's your acquire volatile data. Turn off computer. Is the computer on? No. Remove hard disk. Write protect the suspect device. Acquire non-volatile data. Plan for contingencies and validate data acquisition. So, step one. An investigator needs to identify the best data acquisition method suitable for investigation, depending on the situation the investigator is presented with. These situations include size of the suspect drive, time required to acquire the image, whether the investigator can retain the suspect drive. Excuse me. Example, in case the original evidence drive needs to be returned to the owner, as in case of discovery demand for civil litigation cases, check with the requester, lawyer or supervisor, whether logical acquisition of the disk is acceptable. If not, you may have to go back to the requester. Investigators need to acquire only the data that is intended to be acquired. So remember how we talked about scope of warrants? Sometimes you run into this on that, so you may only be able to pull certain areas of your information. Hold on. Sorry, I didn't want to cough really loud in you guys' ears. So you have your application layer, file system layer, partition volume layer, and disk layer, and it shows logical sparse and full image on that. And then we need to select our acquisition tool. So investigator needs to choose the right tool for data acquisition based on the type of acquisition technique they choose. When it comes to imaging tools, they need to choose the tools that satisfy certain requirements. The tool should not change the original content. That is rule number 1 in digital forensics. Anyway, the tool should log IO errors in accessible and readable form, including the type of error and location of the error. The tool must have the ability to pass scientific and peer review. Results must be repeatable and verifiable by a third party if necessary. So that's, remember how we talked about with the scientific method, you have to be able to go back and do the exact same thing and get the exact same answers. With peer review, that's basically someone who is your peer or third party coming in and reviewing the methods and saying, yes, this passes scientific review. I, as a expert, say that this passes these various checks and balances. The tool should alert the user if the source is larger than the destination. The tool should create a bitstream copy of the original content when there are no errors in accessing the source media. The tool should create a qualified bitstream copy. A qualified bitstream copy is defined as a duplicate except in identified areas of bitstream when IO errors occur while accessing the source media. Step 3, sanitizing target media. There are all sorts of rules for this, so here you go. Investigators must properly sanitize target media in order to any that should read in order for any prior data residing on it to be removed before it is used for collecting forensic data. Post-investigation, they have to dispose the media by following the same standards so as to mitigate the risk of unauthorized disclosure of information and ensure its confidentiality. That's why standard operating procedures, you should have a cycle, and the very last step of your cycle should be the destruction cycle. The following are some standards for median. There's the, you can go look these up and they will tell you NIST, SP 888. A lot of the time you can default to NIST unless it's something that your specific laboratory is required to use, like the DoD, that's the Department of Defense. Then, you know, those require, usually they require you overwrite with a certain program until, you know, everything's gone.
I feel like
go ahead.
sorry. I was just gonna say I feel like they need to fact check this slide set a little bit more because everyone knows Russia has some standards.
Well, okay, what the official document lists, we'll say that. Okay, step 4, acquire volatile data. So volatile data acquisition involves collecting data. It is lost when the computer shut down and restarted. This data usually corresponds to running processes, logged on users, registries, DLLs, clipboard data, open files, etc. Acquiring data from a Windows machine. You can use things like Belkasoft Live RAM Capture, which is a forensic tool that allows extracting the entire contents of the computer's volatile memory and then saves the image files in a .mem format. And there's a little note here. While performing live acquisition, an investigator must be aware of the fact that working on live systems may alter the contents of RAM or processes running on the systems. Any involuntary action performed on the system may potentially make the system inaccessible, which is why you have to make notes about the status and the process, and you have to note everything before you do anything. And then there's an example of Belkasoft Live RAM Capture right there. Enabling write protection on evidence media. So we talked a little bit about this previously, but it's necessary to write protect the suspect drive using write blockers to preserve and protect evidence contained on it. Write blocker is a hardware device or software application that allows data acquisition from the storage media without altering its contents. Block write commands. It blocks write commands, thus allowing read-only access to the storage media. If hardware write blocker is used, you install a write blocker device, boot the system with the examiner controlled operating system. Examples of hardware are like CUR, WeebTech, USB write blocker, and I've used Tableau's forensic bridges. In fact, I had one on my forensic station. And they're basically, you just, you set them up and they have like a swappable drive bay that you set up and it sets things as write blocked, and you pop it in and it blocks it right away. Software write blocker, boot the system with the examiner controlled operating system, activate your write protection, and there's safe block, Mac Forensic Lab write controller, and there's a bunch of other ones too. Acquiring non-volatile data. Non-volatile data can be acquired in both live acquisition and dead acquisition, which mainly involves acquiring data from a hard disk. There's no significant difference in the amount of data acquired from a hard disk between live and dead acquisition methods. Live acquisition of a hard disk is performed by using remote acquisition tools like Netcat and a bootable CD or USB like Kane, while dead acquisition involves removing the hard disk from the suspect drive, connecting it to a forensic workstation, right blocking the hard disk, and running forensic acquisition tools on the disk. So here is one using Windows Forensics Workstation. To acquire forensic image of the hard disk during dead acquisition, you yank your hard drive, connect it to your forensic workstation, enable your write blocker, and run a forensic imaging tool. And there's an example here is FTK Imager. On the workstation, access data FTK Imager is a disk imaging program, and you can download FTK Imager Lite. It's out there in your course documents if you want to see what it's like, which can preview recoverable data from a disk of any kind and also create copies called forensic images of that data. Planning for contingencies. Investigators must prepare for contingencies such as when the hard disk or software does not work or a failure occurs during acquisition. You always have to have a backup plan. Always, always, always. Hard disk acquisition. Investigators must create at least 2 images of digital evidence collected in order to preserve it. If one copy of the digital evidence recovered becomes corrupt, investors can use the other copy. Imaging tools. If you possess more than one imaging tool, such as Pro Discover Forensics or FTK Imager, it's recommended to create the first image with one tool and the second image with the other tool. If you possess only one tool, make 2 or more images of the drive using the same tool. So sometimes you'll see people they'll use this 2 tools, and they'll do 4. So they'll do 2 and 2. It just depends on the lab and how much storage space they have, because when you're doing digital forensics, it's very easy to have accidents. Consider using hardware acquisition tools like UFED or IM-Solo that can access the drive at the BIOS level to copy the data in the host protected area. And then drive decryption. Be prepared to deal with encrypted drives that need the user to provide a decryption key for decrypting. Microsoft includes full encryption features like BitLocker with select editions of Windows Vista and later. But there are also all sorts of different programs that you can use. And people have become a lot smarter with encryption than they used to be. Validation of data. Validating data acquisition involves calculating the hash value of the target media and comparing it with its forensic counterpart to ensure that the data is completely acquired. The unique number or hash value is referred to as a digital fingerprint. As hash values are unique, if 2 files have the same hash value, they are 100% identical, even if the files are named differently. Utility algorithms that produce hash values include CRC32, MD5, SHA-1, and SHA-256. So this is validation with Windows validation methods. Windows computers come with PowerShell utility, which you can use commandlets on. You can do get file hash commandlet, which computes the hash value for an evidence file by using the specified hash algorithm. This hash value is used throughout the investigation for validating the integrity of the evidence. Investigators can also use commercial computer forensics programs, which have built-in validation features that can be used to validate the evidence files. For instance, ProDiscover's .eve files contain metadata in segmented files or acquisition files, including the hash value for the original media. When you load the image to ProDiscover, it compares the hash value of the image to the hash value of the original media. If they do not match, the tool notifies that the image is corrupt, implying the evidence cannot be considered reliable. So you can see down here, get file hash, and then you can see their hash right there. And this is with PowerShell. In most computer forensic evidence tools, raw format images do not contain metadata for raw acquisitions. Therefore, a separate manual validation is recommended during analysis. When you do the validation with Geiger, there's a file that it pops up, and you tell it, MD5, SHA, and you can look at that file and it'll show you the 2 hash values, so you can see that they are indeed validatable. All right, summary. So what did we talk about? Data acquisition fundamentals. What types of data acquisition are there? Different types of data acquisition formats, detailed discussion on data acquisition methodology. And then in the next model, not next week. Next week is spring break, no class. Next time we meet, we'll discuss defeating anti-forensics techniques. Okay, so that is it for this particular module. I'm going to go ahead and let me hit stop share here. I'm going to stop the recording here, but then I'm going to talk to you guys a little bit about a few things before spring break, okay?